Welcome back, students. In today's session, we'll be learning about deadlock avoidance. So, deadlock avoidance requires that the system has an additional information regarding the processes, and we are calling it as primary information. In primary information, the system must know about the processes that will be requiring the maximum number of resources to complete their execution. And deadlock avoidance algorithm will dynamically examine the resource allocation state to ensure that there can never be a circular wait condition arising. Resource allocation state here is defined by the number of available and allocated resources and the maximum demands that the processes are making here. So as prior information, we should have this information about the processes that will be using maximum number of resources beforehand. We should have this information, and this deadlock avoidance mechanism is based on prior information. So here we have a save state. Every now and then we are saying that it must be the system must be in a save state. So what actually a save state means here? Let us see. When a process requests any available resource, the system must decide if an allocation can be done immediately, and doing so, it should not leave the system in an unsafe state. That means it should be sure that the system is in safe state. Now, in order to make sure that the system is in safe state, there must exist a safe sequence. Now, by a safe sequence, we mean that the sequence of processes in a particular order. Say, for example, P1, then P2, then P3, and so on till the last process. It will be called as a safe sequence for the current allocation state. If for each process, the resource request that a process can still make and can be satisfied by currently available resources plus the resources held by all other processes in the system. Following the criteria that a process, suppose a process PI is requesting for a resource, right? And this request can be satisfied. That means we can allocate resources to this requesting process by making use of available resources as well as the resources that are already allocated to some other process, say PG. So here we have a condition that PJ is less than PI. Okay, so that is here. Let us elaborate this point. If the process PI request needs are not immediately available, then PI can wait until PJ have finished. So if a process PI is requesting for the resources and it cannot be satisfied immediately, then in that case, this requesting process PI can wait until all other processes, say PJs, have finished their execution. First case. Second case, when PJ is finished, PI can obtain needed resources, execute, return allocated resources, and then terminate. When other processes have finished their execution, then this requesting process PI can obtain the needed resources and it will complete its execution. After completion, it must return the allocated resources and then terminate. When process PI terminates, process PI plus 1, that means a process ahead, the next process, can obtain its needed resources and the chain continues. forming a safe sequence of processes. I hope you have understood this safe sequence. That means this chain will continue. If process P1 is requesting the resources and the resource is granted, then only P2 can request for the needed resources. Then P3 will request the needed resources. So this will form a safe sequence. This ultimately leads to the safe state of the system. Now, if a system is in safe state, that means there are no deadlocks. But if a system is in unsafe state, then there arises a possibility of deadlock. Deadlock avoidance mechanism ensures that the system will never enter an unsafe state. So deadlock avoidance mechanism is making sure that your system is never entering an unsafe state, because when it enters an unsafe state, the possibility of deadlock occurrence can be there. Now here we have a diagram showing the relationship between safe, unsafe, and deadlock state. Okay? So when the system is in safe state, you may notice that there is no deadlock. But if the system enters in unsafe state, there is a possibility of deadlock occurrence. Now, for a single instance of a resource type, use a resource allocation graph. For deadlock avoidance, if there is a single instance for every resource type, it is better to use resource allocation graph to make sure that the system is in safe state. For multiple instances of a resource type, we can use Banker's algorithm. Now here we have Banker's algorithm, resource allocation graph. Now this introduces a new kind of edge called a claim edge. So here we are just transforming resource allocation graph in how we can design this. Okay. So see, we are now introducing a new edge in the resource allocation graph that is called as a claim edge. Now this claim edge can be drawn like this. It is just initiating from a process and going outwards to a resource. Okay, so a dotted arrow is indicated from a particular process towards a particular resource type. Now, this indicates that the process CI may request a resource of type RG. So this claim edge is indicating that in near future, this process may claim, may request for this particular resource type. Okay, so it is indicated by dash line provided with an arrow here. A claim edge converts to a request edge when a process requests a resource. So until it is not converted into the request edge, when the process makes a request, then only this claim edge gets converted to a request edge. Okay. Now a request edge converts to an assignment edge when the resource is allocated to the process. The process is requesting for a resource, but if it has not been allocated a resource immediately, then it will be like that only. Okay? But then request edge will be transformed to an assignment edge only when resources are allocated to the requesting process. When a resource is released by a process, this assignment edge gets converted back to claim edge again. A resources must be claimed a priority in the system. So this is the binding here. The resources that will be claimed, we should have a prior information about that. Now here is a resource allocation graph with the claim edges. Now you'll better understand what I was saying about C. Process PI is having this dashed line arrow. This is a claim edge indicating that in future P1 may request for a resource R2, right? So similarly here we are also having this P2 process having a claim edge. So this may also request for resource R2. Okay. Whereas if an edge goes from a process towards a resource, a solid arrow, so this is called as request edge. Okay. So here actually P2 is requesting for a resource R1, right? Now when the request is granted, at that time you'll be having this kind of edge. So this edge will be initiating from a resource type towards the process. So this is an assignment edge. Clear? So we are having three type of edges here, right? So the request edge, claim edge, and assignment edge. I hope you have understood this. Now this graph shows an unsafe state in the resource allocation graph. This will be an unsafe state in the resource allocation graph. Let us see how. See, very interesting. P1 here is having a claim edge over R2 resource, right? R2, right now we don't know how many instances are there for each resource type. In the system, we are having two resources, R1 and R2, and there are two processes, P1 and P2. Now, P1 is having a claim edge towards R2, right? Whereas the resource R2 has already been allocated, has been assigned to P2, right? So this resource is allocated to P2 here. Now P2 holding this request R2 is making a request for resource R1, right? And R1 resource is already assigned to P1. Okay, so the system here is in unsafe state. If there exists a single instance, then the system enters in an unsafe state because P2 is already holding a resource and is also making a request for another resource here, right? Which can't be granted initially because it is already allocated to P1 process. Now suppose that P1 or PI in general, we are making these notations, PI, RJ, okay? Request a resource RJ. The request can be granted only if converting the request edge to an assignment edge does not result in the formation of a cycle in the resource allocation graph. I hope you are following me. See here, when a process, we have to be very careful about this, when a process requests a resource type, right? So this is a requesting edge. The requesting edge gets converted into assignment edge when the request is granted. Okay, so you have to check whether this allocation of a resource to a process does not result in the formation of a cycle in the resource allocation graph. So this is the technique to make sure that cycle doesn't exist in the system. Okay, so we have to avoid cycles in the resource allocation graph. So converting the requesting edge to an assignment edge must not leave this resource allocation graph with a cycle. Okay. Now we'll move to the next point, that is Banker's algorithm. So here we have multiple resource types. In case you are having multiple resource type instances, that is multiple instances of the resource type, then each process must have a priority claim maximum use. That means whatever maximum need of a process is there to use the resources, it should declare it beforehand. When a process requests a resource, it may have to wait. When a process gets all its resources, it must return them in a finite amount of time. So see here, what compulsion we are putting here, what rules we are applying here. A process, when a process requests a resource, it may have to wait, right? The request can't be granted immediately since we have to check the instances available, the resources whether they are available for further allocation. Okay. And when a process gets all its resources that are required for its execution, after execution, it must return them in a finite amount of time. It should not hold the resources indefinitely because it will cause starvation for other processes. Okay? So we are putting a rule here that it should return the resources, whatever resources have been allocated to it, it should return it in finite amount of time. Okay. Now here we have the data structure for Banker's algorithm. Let N be the number of processes in the system and M be the number of resource types. So here we have available, which is a vector of length M. See here, M is the number of resources. So if you are using M as the index for this available vector, it means it will indicate that how many resources are available for use. See here, if available of J is equal to K, it means that there are K instances of resource type Rj available. Then we have next data structure, that is max, which is a matrix of n by m size. If max of I, j is equal to K, then process Pi may request at most K instances of resource type Rj. See here, J is an index we are using to indicate resources. I, we are using an index for indicating processes. Okay. So if max of I, j is equal to some k, some number. Now k obviously will be holding certain integer value for k, right? So it indicates that process Pi may request, it can make a demand for at most K instances of this resource type Rj. Okay. So this is what we are expecting from the processes, now to declare and try what will be their maximum usage of resources. So it should declare for each process their maximum usage for every resource type should be indicated in advance. Then next comes allocation. It is also an n by m matrix here, but if this will give us an idea that how many resources are allocated to the process. So if allocation I, j is equal to k, then it means that process Pi is currently allocated k instances of type Rj resource. Okay, so available max allocation. How many number of instances of a resource type is available here? We'll come to know about from this. Then maximum need of the processes. How much allocation has been done? How maximum need is declared, but out of that, whether all of the needed resources have been allocated to the processes or some of the resources have been allocated, and still it requires some more resources to complete its execution will be indicated here by the need matrix. So it is also an n by m matrix here. If need of I, j is equal to k, then it means process Pi may need k more instances of resource Rj to complete its task. So here we can make a calculation for need matrix using this formula. If we know the max matrix, maximum need of the process, this is declared beforehand, right? This will be calculated after, this will be calculated after allocating some of the requests, okay? After satisfying some of the requests of the processes. So we'll come to know about the allocation. So if we subtract allocation matrix from max matrix, then we can find what is the remaining need of the process. I hope you have followed this. Coming to the next part of our session here is deadlock detection. For deadlock detection, the system must provide an algorithm that examines the state of the system to detect whether a deadlock has occurred. Deadlock detection, detecting the deadlock in the system. Okay, so there must be an algorithm which continuously examines the state of the system to find out whether a deadlock has occurred. An algorithm to recover from the deadlock as well is required here. Not only detection, the system must be able to recover from a deadlock situation also. So for that, you require an algorithm as well here. A detection and recovery scheme requires various kinds of overhead, various kinds of computation, such as runtime cost for maintaining necessary information and executing the detection algorithm, and potential losses inherent in recovering from a deadlock. Obviously, you can recover some of the stuff. You can recover the state of the processes, some of the processes, right? Complete recovery is not possible. So there will be potential losses if the system goes in a deadlock situation and you're trying to recover it from that. Now here we have single instance for each resource type. Now for single instance for each resource type requires the creation and maintenance of a wait for graph. Right? Now a wait for graph is actually a variant of resource allocation graph. So there are some minor differences between resource allocation graph and wait for graph. Now this wait for graph is obtained by removing the resource node from the resource allocation graph and collapsing the appropriate edges. So here what changes we are going to do in resource allocation graph is removing the resources node, removing those rectangular nodes in the resource allocation graph, and further deleting those appropriated edges. So this wait for graph will have all of the nodes as processes only. And if you encounter this kind of situation that where you find a process Pi is having an edge towards process Pj, it indicates that process Pi is waiting for Pj to finish because Pj is executing and is holding a resource that process Pi needs. Okay. No. This periodically invokes an algorithm that searches for a cycle in the graph. So this wait for graph, an algorithm runs all the time at the back end and it searches for a cycle in the graph. If there exists a cycle, then surely there exists a deadlock. Now, an algorithm to detect a cycle in a graph requires an order of n square operation. So the time complexity for this algorithm to detect a cycle is n square, where n is the number of vertices in the graph. Now here we have resource allocation graph and wait for graph side by side. So you may notice the difference between these two. In resource allocation graph, we have these square boxes that these are the nodes for resource and appropriate edges are there. So if we are removing these nodes, these square boxes from this, so the formation of wait for graph is there. It will result in the formation of wait for graph. And we are deleting appropriate edges also. See here, how we are deleting appropriate edges? See, P1 is requesting for resource R1, whereas R1 is held with P2. So obviously P1 will be waiting for P2, right? So see, the same assignment has been done here. And we have collapsed these two edges and we have removed this particular node from it. Similarly, here P2 is requesting for R3, whereas R3 is with P5. So P2 will be waiting for P5 and so on. The complete graph is constructed here. I hope you are able to follow me. Now, for multiple instances of a resource type here, we require the data structure such as available, allocation, and request. Just like in Banker's algorithm, so here we'll be keeping a data structure as available. So this is a vector of length m that will indicate the number of available resources of each type. Allocation here is will specify the number of resources of each type that are currently assigned to each process. And request is a matrix that indicates the current request of each process. So here, if request ij is there is equal to k, it indicates that pi is requesting for k more instances of type rj. Okay. Further, now, when and how often to invoke the detection algorithm, it depends on. See, we require deadlock detection algorithm. In case of deadlock detection, we are invoking an algorithm to find out the cycle to detect the deadlock. Okay. So how often, how frequently we require this detection algorithm? It depends on two things. Firstly, how often is the deadlock likely to occur? That means what is the possibility of deadlock to occur frequently? Okay, first thing. Second thing, how many processes will be affected by deadlock when it happens? It is also necessary that we should analyze how many processes will be affected by the occurrence of deadlock. Okay? If the detection algorithm is invoked arbitrarily, there may be many cycles in the resource graph. And so we would not be able to tell which one of the many deadlock processes caused the deadlock. See, we need to find the culprit process who is actually responsible for the deadlock occurrence, who is causing the deadlock situation. So if this detection algorithm, we are invoking it, we are calling it arbitrarily at any time, right? So there may be many cycles in the resource allocation graph. And we would not be able to find out the process who has resulted in the deadlock situation, right? Now, if the detection algorithm is invoked for every resource request, then such an action will incur a considerable overhead in computation time. First thing is, if we are invoking that detection algorithm arbitrarily, there may be many cycles in the resource graph, and this will result in no conclusion about the process is causing the deadlock. Right? Secondly, if we invoked it for every request that the process makes, then it is actually an additional overhead and it consumes computation time. So a less expensive alternative is to invoke the algorithm when CPU utilization drops below 40%. Okay. So when CPU utilization goes below 40%, so here it is advised that a deadlock detection algorithm should be invoked. But this is based on the observation that a deadlock eventually cripples system throughput and causes CPU utilization to drop. How we are calculating this if the CPU utilization goes below 40%? So if the CPU utilization is less, it means that most of the processes, they are not able to complete. We are not getting maximum throughput. A throughput is a metric that we are measuring the number of processes finished their execution in the given time. That will contribute to throughput. So if throughput is less, the CPU utilization ultimately drops out. The next part here is recovery from the deadlock. Up till now we have discussed the deadlock prevention, deadlock avoidance, deadlock detection. Now, what to do if deadlock occurs, right? How to recover the system. So there are two approaches here for recovery from deadlock. First, process termination. And second, we have is resource preemption. Let us see it one by one. Process termination. In process termination, again, we have multiple factors to consider. So here, abort all deadlock processes is one of the options available. If we are terminating the processes, we can terminate all of the deadlock processes. So this process will break the deadlock, but at a great expense. What expense we are paying here? All of those processes which we can continue to execute by resolving or by terminating some of the processes, then also we are just stopping abruptly their execution too. That means in this time, your throughput is zero. The system throughput will be zero if you are terminating all of the deadlock processes. Okay? So it is simple to do, but at a great expense. Next option is abort one process at a time until the deadlock cycle is eliminated. And this seems to be a better option than the first one, isn't it? So this approach incurs considerable overhead. No doubt, it will take additional computation, right? It will be an overhead over the system for computation. But since after each process is aborted, a deadlock detection algorithm must be re-invoked to make sure whether the cycle is removed or whether any processes are still deadlocked. Okay, so additional overhead in these terms only, that it requires frequent invocation of deadlock detection algorithm, okay, but seems to be a better approach. Now, many factors may affect the process. Many factors may affect which process is chosen for termination. Now, another choice or another, we can say, a problem for choosing a process for termination is there. So there can be many factors based on which we can decide which process can be chosen for termination. First thing is, what is the priority of the process? You have to check for the priority of the process. Then how long has the process run so far, and how much longer will be the process need to run before completing its task? You have to analyze this. The system will analyze this, how far it has completed its execution, and how much more time it will be needing for further execution in order to complete its execution. Okay. Then, how many and what type of resources has the process used? It can be another factor here. Then, how many more resources does the process need in order to finish its task? Then, the number of processes will need to be terminated. Next decision you'll have to make on how many number of processes among the deadlock processes will be terminated. And is the process interactive or a kind of batch process? We will have to find out the answers for these, and then you will be able to decide which process to terminate. The next approach for deadlock recovery is resource preemption. We know the meaning of preemption, right? Before the process willingly release the resource, we are just prompting the process to give away the resource that it is holding. Okay, this is resource preemption. We are taking it back forcefully. So with this approach, we successively trim some resources from processes and give these resources to other processes until the deadlock cycle is broken. In this case, what we are doing? We are taking some of the resources from the processes and we are allocating it to other processes so that they can continue with their execution. If they completed their execution, they will release the resource. Hence, the deadlock cycle will be broken here. When preemption is required to deal with deadlock, then three issues need to be addressed. These three issues are selecting a victim. So here, which resource and which processes are to be preempted? You have to select a victim from the processes whose resources you will be taking back. Okay. Next issue here is rollback. If we preempt a resource from a process, what should be done with that process? What should be done? Whether its state has to be rolled back or it will be terminated, right? Okay. If it has been rolled back to the previous state, then it will resume its execution from the previous state. If it has been terminated, then next time it has to be started from the beginning. Okay. So clever decision has to be made here. And the last issue here is starvation. How do we ensure that starvation will not occur? If we are preempting resources from the same process again and again, so it is more obvious that this process whose resources are being preempted continuously will face a starvation. And how far we are able to make sure that the starvation will not occur? That is how we can guarantee that the resource will not always be preempted from the same process. See, if we are preempting the resources from the same process, the process will enter starvation state, right? There will occur starvation. So we have to be sure that every time we preempt the resource, it must not be the same process from which we are taking back the resources. I hope you have understood the concept here. Now here we have the summary of the points that we have studied so far in deadlock and deadlock detection, deadlock prevention, deadlock avoidance, as well as the recovery mechanism. So point to remember here is the four necessary conditions that must hold in a system for a deadlock to occur. That is mutual exclusion, hold and wait, no preemption, circular. Then the four principles for dealing with deadlock is using some protocols to prevent the deadlock situation, to avoid the deadlock situation, and to ensure that the system will never enter in a deadlock state. Right? Then we also allow the system to enter a deadlock and we recover from it. That is, we are detecting the deadlock. The system will enter into the deadlock and will detect it and then recover from the deadlock situation. And the last thing is doing nothing, just ignoring the problem and letting the user or the system administrator to handle the situation, which is mostly done by Windows and Unix operating systems. Now, to prevent deadlock, we can ensure that at least one of the four necessary conditions never holds. I hope you have followed this complete chapter. That's it for today. If any queries, you can put up to my classroom and we can discuss it there. Okay, then I'll meet you with the next topic in the next lecture. Till then, take care.